So, if you ask an AI to write a story about a bank, it doesn't actually picture a marble building with vaults.
No, it really doesn't.
Right. I mean, it doesn't picture a teller or a vault door or even the muddy edge of a river.
Exactly. That's entirely a human way of visualizing things.
Because when you hit enter on that prompt, the system actually pictures a multidimensional string of decimal.
Yeah, just raw math.
Something like a 0.45 and negative 0.12, 0.88. And today, we are tearing down the magic trick of artificial intelligence.
Which is so overdue.
We're getting entirely past this idea that there's some, ghost in the machine, or that these systems are just hallucinating black boxes that we can't possibly comprehend.
And that is an incredibly necessary pivot for anyone listening right now who wants to actually use these systems effectively.
Definitely.
Because right now, there is a massive divide between the people who are just, passive consumers of a chat interface.
Just typing and hoping for the best.
Right, and the people who actually understand the underlying structural mechanics.
Yeah.
If you don't understand the bones of how these systems parse information, you're entirely at the mercy of marketing hype.
Completely.
But if you can see the blueprint, if you know what happens to your data the millisecond you hit send well, you can actually start architecting your own workflows.
And that is the exact mission for this deep dive. For you listening, this is your shortcut.
Yes.
We've got our hands on a synthesis of some heavy-hitting architectural documents today.
Some really dense stuff.
Very dense. Specifically, we're looking at a structural breakdown titled The AI Architect's Blueprint Structural Mechanics of Generative Agents.
Fantastic document.
It really is. And it pulls heavily from the structural mechanics outlined in chapters 2 and 4 of Building Generative AI Agents.
Ooh.
So our goal today is to take you on a very specific journey. We want to track the complete end-to-end life cycle of one single AI action.
From absolute scratch.
Yes, from scratch. We're going to figure out how a raw, messy, chaotic pile of human data eventually turns into a reasoning agent that can, autonomously execute complex tasks.
And to do that, we really have to start at the absolute bottom of the stack.
Let's do it.
Because before we can talk about agents or tools or Python execution, we have to understand the fundamental reality of how a machine perceives our world.
Right, which goes back to my bank example.
Exactly. Because as you hinted at, the machine does not read words, it reads mathematics.
Right, and to even get to the math, we have to talk about what it's trying to read in the first place.
The raw materials.
Yeah, the materials we're looking at describe this as the unstructured data problem.
It's a huge problem.
I mean, when we think about data, most of us picture an Excel spreadsheet. Neat columns, clear rows, everything perfectly categorized.
Which is a beautiful fantasy.
Right, because that is not what human knowledge actually looks like, is it?
Not at all. I mean, structured data like that spreadsheet is actually a tiny, tiny fraction of the information in the world.
Just a drop in the bucket.
The vast majority of human digital exhaust is completely unstructured. Just think about the sheer chaos of it.
No, it's a mess.
We're talking about billions of Wikipedia articles.
Yeah.
We're talking about decade-old email archives buried in corporate servers, sensor logs from manufacturing equipment, which are just endless streams of timestamps and pressure readings.
Not to mention the really messy stuff, like Reddit threads full of sarcasm and slang and, just broken grammar.
Exactly.
Or client proposals that are half text, half weirdly formatted images.
Yeah.
Internal company wikis that haven't been updated since, 2015.
It is a swirling, chaotic web.
Yeah.
And if you want to build an intelligence, you have to feed it the sum total of human knowledge, right? But human knowledge is a disorganized mess.
So the very first architectural hurdle is translation.
Precisely.
How do you take a sarcastic comment on a message board or a dense academic research paper on molecular biology and translate it into a format that a computer processor can actually calculate?
And this brings us back to those decimals you mentioned at the start.
Math.
The math. The translation process converts human language into something called embeddings.
Okay, yes. I've heard this term thrown around a lot in tech circles.
It's quite the buzzword right now.
It is, but the way our blueprint document breaks it down is fascinating. It says an embedding isn't just a label. It's a dense vector representation.
Okay, let's strip away the jargon there, because dense vector representation scares people off.
It sounds like a college physics class.
It really does. Let's explain the actual mechanism. An embedding is simply a mathematical coordinate in a massively multidimensional space.
Okay, stop right there. Because when you say mathematical coordinate, my brain immediately goes to a map.
Sure, like a globe.
Yeah, latitude and longitude, x and y. 2 dimensions, maybe 3 if we add depth, like an airplane's altitude.
Right.
But you're saying multidimensional space. What does that actually mean in practice?
It means we have to stretch our imagination way beyond physical geometry.
Okay, I'm trapped.
Instead of just X, Y, and Z, imagine a coordinate system that has hundreds or even thousands of distinct axes.
Thousands of direct.
Yes, a modern AI model might map concepts in a 1024-dimensional space.
Oh, wow.
And every single dimension represents some microscopic latent feature of meaning. We as humans cannot visualize a 1024-dimensional graph. It's impossible.
Yeah, my brain just broke trying to picture that.
But a computer can calculate distances within it perfectly.
So let me make sure I'm getting this. When I type the word bank, the AI translates that into a list of 1,024 numbers.
Correct.
And that string of numbers, like the 0.45, negative 0.12, 0.88, is literally just a set of GPS coordinates pointing to one highly specific location in that massive mathematical universe.
Precisely. That is exactly what an embedding is.
That is wild. Now, why go through all this trouble? Why not just use a dictionary?
Because of a concept called semantic proximity. And this is crucial. This is how the machine actually understands meaning.
Semantic proximity.
Yes. In this massive coordinate space, things that have similar meanings are placed physically or mathematically close to each other.
So meaning is just a neighborhood.
Exactly. Meaning is just proximity.
I love that.
If I plot the coordinates for bank, as in a financial institution, it is going to be sitting in a mathematical neighborhood right next to the coordinates for vault, money, interest rate, and loan.
Right. But wait, what if you are talking about the bank of a river? Because the letters B-A-N-K are exactly the same. How does it know the difference?
Because the model captures context before a response is ever generated.
Okay.
The phrase riverbank maps to a completely different set of coordinates than investment bank.
Oh, so it literally sends it to a different neighborhood.
Exactly. The coordinates for the river version will be placed closely to water, mud, stream, and erosion.
That's brilliant.
The AI doesn't have a soul. It doesn't have a picture of a river in his mind. But it knows exactly where that concept lives in relation to every other concept in the universe.
So if two words hang out in the same neighborhood, the AI mathematically assumes they are related.
That's the core of it, yes.
This makes so much more sense now. But having a mat is only half the battle, right? You still need a way to read it.
You do.
And for a long time, early AI systems read text just like we do, sequentially, word by word, left to right.
Which is incredibly inefficient for a machine.
Right. Why is that?
Well, think about how human language actually works. Sometimes, the most important word in a sentence is at the very end, and it completely changes the meaning of the word at the very beginning.
Oh, like a twist ending to a sentence.
Exactly. So if you read sequentially, you have to constantly hold everything in short-term memory and revise your understanding on the fly as you read each new word.
Which brings us to the massive breakthrough, the architecture that basically birthed modern generative AI.
To transform it.
The transformer. And specifically, a mechanism inside it called self-attention. This is where sequential reading just goes completely out the window, right?
Yes, entirely. Transformers use parallel processing.
Okay, unpack that.
Instead of reading word by word, the self-attention mechanism looks at every single word in your prompt simultaneously.
All at once.
All at once. It weighs the importance of surrounding tokens all at once, instantly calculating the structural dependencies between them.
Okay, let's use a tangible example to ground this, because this is where the math gets really cool.
Let's do it.
The materials we're referencing use the word bark. Similar to our bank example, bark could be the sound a dog makes, or it could be the outside of a tree.
Right.
Let's say our sentence is, the loud dog continued to bark at the thick branch of the tree.
A perfect stress test for the machine.
Right. So the AI isn't reading left to right, it's looking at the whole sentence at once.
Yes.
The self-attention mechanism is calculating mathematical gravity-like attention weights between every single word and every other word.
Simultaneous calculations.
And our blueprint shows that when the model evaluates the connection between dog, loud, and bark, it assigns a massively high mathematical weight. It scores it a 0.92.
Which is huge. That 0.92 is a siren going off in the math. It is the system saying, hey, these coordinates are heavily pulling on each other. The context of bark here is almost entirely dependent on the presence of dog and loud.
But, and this is the brilliant part, in that exact same sentence, The model calculates the weight between bark and tree and bark and branch,
Right.
and it assigns them a tiny, insignificant weight of just 0.04.
Which is the system essentially dismissing them.
It just ignores them.
Right. It proves that the AI knows exactly which version of bark is being used. And it does this not by understanding biology or animals.
But by doing the math.
Yes, by instantly doing the math on the relationships of every coordinate simultaneously.
So I have a question here, just playing devil's advocate for you listening. If it has to calculate the relationship between every single word, if I feed it a 100-page document, is it literally calculating the mathematical weight between the word on page 1 and the word on page 100?
Yes. Every single token to every other token.
That sounds exhausting.
It is. And that is why we refer to this later in the document as the attention bottleneck. The computational power required to do that is staggering.
Yeah.
You double the length of the text. You don't just double the amount of math, you quadruple it.
Oh, wow.
It scales quadratically. Every single token must calculate its relationship to every other token. But that is the foundational bedrock of how it reads.
Okay, so we have established the foundation. We know how the machine translates human chaos into embedding coordinates.
We've got the map.
We've got the map. We know how it reads those coordinates using the simultaneous math of self-attention. Now, we actually have to build the engine itself. We have to decide what shape this artificial brain is going to take.
Because form dictates function.
Right.
The architecture you choose entirely depends on what you want the system to achieve.
And the structural breakdown gives us 3 distinct types of transformer models. Let's not just list them. Let's really figure out how they differ mechanically.
Good idea.
The first one is the autoregressive model. This is the architecture behind the most famous systems, like the GPT family.
The big ones, yeah.
Its processing direction is described as unidirectional, left to right.
Right. Now, even though the attention mechanism looks at the whole prompt at once, the generation mechanism in an autoregressive model only moves forward.
Okay, so it only creates in one direction.
Exactly. It predicts the very next token based strictly on the tokens that came before it. Once it generates a word, that word becomes part of the history, and it guesses the next one.
So its core strength is text generation. It's basically a prediction engine.
Exactly. I like to think of an autoregressive model like a jazz musician improvising a solo.
Oh, I like that.
Think about it. The musician plays a note. They can't unplay it.
Right, it's out there in the air.
Yes. They have to build the melody forward in time, generating the next note based strictly on the progression of notes they just played a second ago. They're generating something entirely new, moving left to right through time.
That is a great analogy, the jazz musician. Okay, so contrast that with the second architecture autoencoding model. A major example here is BERT. Instead of moving left to right, it processes data bidirectionally. It looks backward and forward simultaneously.
And because of that bidirectional structure, its core strength isn't generating new text. It is actually terrible at writing you a poem.
So no jazz solos.
No jazz solos.
Yeah.
Its core strength is understanding and analyzing the text that is already there. It excels at things like classification, sentiment analysis, and named entity recognition.
Wait, pause on that last one. Named entity recognition, or NER, what does that actually look like in practice? Let's ground that.
Sure. Imagine you are a law firm and you have a 500-page contract. You don't want the AI to write a new contract. You want it to scan the existing one and extract every single time a specific corporate entity is mentioned, alongside the exact dollar amounts associated with them.
Okay, I see.
That is NER.
Ah, okay. So if the autoregressive model is the jazz musician improvising forward, the autoencoding model is more like a detective analyzing a crime scene.
That's exactly it.
The detective isn't trying to commit a new crime. They walk into the room and they look at the whole scene at once. They look backward at the footprints, forward at the broken glass, analyzing the entire context simultaneously to classify exactly what happened and extract the specific evidence.
That is spot on. The jazz musician generates, the detective classifies.
Got it.
And then, just for completeness, our source materials do mention a third type hybrid models, like T5.
Right.
These are essentially an architectural compromise. They combine both processing directions for broad, general-purpose natural language applications.
Okay, so let's say I'm a developer. I've chosen my shape. I want the jazz musician because I want to build a system that generates dynamic responses for my users.
Makes sense.
Now I have to figure out where this brain is going to physically live. And this is a massive operational decision.
It's huge.
The materials lay out a deployment strategy matrix.
It's the classic build versus buy dilemma, but with massive implications for privacy and performance.
Let's walk through them. The first path is deploying via proprietary LLMs. This is your GPT-4, your Claude. You are paying for a subscription or an API. But the major flag here is data privacy. The document lists it as a cloud risk.
And let's explain why that's a risk. When you use a proprietary API, your data physically leaves your network.
It goes out into the ether.
It travels across the internet to a server owned by another company, gets processed, and the answer is sent back. If you are a defense contractor or a healthcare provider dealing with patient records, that is often a non-starter.
Because of compliance.
Exactly. You cannot legally let that data leave your secure environment.
But the trade-off is performance, right? You get access to the absolute state-of-the-art reasoning ceiling. You are essentially renting time on a multi-billion-dollar supercomputer.
Right. You get the best of the best, but you sacrifice control.
Which leads us to the second path, open source LLMs.
Here, the financial model flips completely.
It does.
There's no ongoing API cost, but there is a massive initial compute and hardware cost. You have to buy the servers to host it yourself, which is incredibly expensive up front.
Right. But the privacy is absolute. You can literally air-gap the system.
Yes. Air gapping meaning you can physically disconnect the server from the internet. The data never leaves the room.
That's ultimate security.
And because the architecture is open source, you have full access to customize the internal plumbing of the model itself. The performance is near state-of-the-art, provided you have the world-class engineering talent on payroll to actually run it and maintain it.
Which is a big if. Now, the third path is the one I find most fascinating because it really feels like where the industry is heavily pivoting. Small language models, or SLMs.
Oh, this is the frontier.
The hardware cost is incredibly low. These are designed to run on edge compute.
Right. And edge compute meaning the processing happens right on the device itself on your smartphone or on your local laptop, rather than in a massive remote server farm.
So privacy is incredibly high because it never leaves your phone.
Exactly.
But here is what I don't quite grasp yet. The materials state that massive models give you broad, generalized intelligence. They know a bit about everything.
Yeah.
But small language models sacrifice that broad intelligence to become highly targeted. How do they actually do that? I mean, do developers just go in and delete parts of the brain? How does it get smaller but stay smart?
That's a really great question about the underlying mechanism. It comes down to parameter counts and training data.
Okay.
A parameter is essentially a synthetic synapse in the artificial brain. GPT-4 has over 1 trillion of them.
1 trillion.
1 trillion. That's why it can write a Shakespearean sonnet and then immediately debug a complex Python script and then translate ancient Greek. It has massive generalized knowledge.
Right, because it has enough synapses to hold all those different neighborhoods.
Exactly. But a small language model might only have 7 billion parameters. To make it smart at that small size, developers use a process called parameter pruning, and they hyper-focus the training data.
Pruning, like trimming a tree.
Exactly. If I'm building an SLM for a hospital to triage patient symptoms, I don't train it on Wikipedia's entire history of 16th century poetry.
Right, doesn't need to know that.
I only train it on medical texts. I curate the neighborhood.
So it becomes a savant. It's totally useless if you ask it for a cake recipe, but it is a genius at diagnosing a fever.
Exactly. And because it's so small, it eliminates cloud latency. It doesn't have to beam data to a server and wait for a response. It processes instantly on your phone. For targeted enterprise workflows, SLMs are the future because they vastly reduce overhead.
Okay. So we've chosen our engine. We've deployed it. Let's say we're using a proprietary API just to keep it simple.
Okay.
We have a powerful, generic, autoregressive model. The jazz musician, it's a blank slate, but right out of the box, it's highly probabilistic. It's basically a very sophisticated autocorrect.
That's a good way to put it.
How do we actually bend this chaotic machine to do exactly what we want reliably?
This is where we transition from the raw science of the architecture into the art of steering the model. The materials call this architectural customization routing.
Okay, routing.
Before you do anything, you have to diagnose your specific problem. What is the actual limitation of the base model that you are trying to overcome?
And the blueprint gives us a clear fork in the road here. Let's say your problem is tone. You need a specific style or a very specific output format. The route you take here is called fine-tuning.
Right. Let's explain the mechanism of fine-tuning. Remember how we said the model is full of parameters, those synthetic synapses?
Yeah.
Fine-tuning actually goes in and permanently adjusts the internal weights of those synapses using a smaller, highly curated data set.
So an example the text gives is legal drafting.
Right. You take a base model and you feed it 10,000 highly specific legal contracts. As it reads them, it slightly shifts its internal embedding coordinates. It learns the specific vocabulary, the cadence, the exact formatting of legal jargon. To go back to your analogy, fine-tuning is like sending our jazz musician to classical music conservatory. You are fundamentally changing their internal vocabulary and the style in which they play.
You're permanently changing the brain.
Yes, permanently.
But what if you take the other path on the fork? What if your problem isn't tone or style? What if you need the AI to know brand new, up-to-date facts or highly confidential proprietary data that wasn't in its original training?
If that's your problem, fine-tuning is actually the wrong choice.
Wait, really? Why wouldn't you just fine-tune it on the new facts? Just teach it the new stuff.
Because language models are terrible at treating fine-tuning data as absolute factual memory. They treat it as stylistic influence.
Oh, I see.
If you fine-tune it on a list of employee phone numbers, it might just learn what a phone number looks like and start hallucinating fake numbers that sound right.
Because it's a jazz musician. It's just riffing on the idea of a phone number.
Exactly.
Yeah.
It's improvising.
Ah.
To solve the factual data problem, you don't change the brain. You use RA, Retrieval Augmented Generation.
Okay, argy.
This is arguably the most critical enterprise architecture in use today.
Let's really break this down because it sounds intimidating. The structural diagram visualizes R as a separate vector database pointing an arrow into the main LLM node. Can you explain a vector database to me like I'm 5?
Sure. Imagine a massive library where the books aren't organized alphabetically by author or by the Dewey Decimal System.
Why?
Instead, they're organized purely by semantic meaning, by those multidimensional coordinates we talked about earlier. That is a vector database. It stores your company's private documents as mathematical coordinates.
Okay, so it's a library of neighborhoods. So how does R actually work at runtime?
Let's say you ask the AI, what is our company's Q3 revenue?
Right.
The RIG system intercepts your prompt before it ever reaches the AI brain. It takes your prompt, converts it into coordinates, and throws a mathematical dart into your private vector database.
Oh, that's cool.
It finds the 3 documents closest to that coordinate meaning, the documents about Q3 revenue.
Right.
It pulls those 3 exact documents out, bundles them together with your original question, and hands the whole package to the AI brain.
Wow.
It says, answer this user's question, but only use the information in these 3 documents I'm handing you.
So if fine-tuning is sending the AI to law school to permanently change how it thinks, RG is just handing the AI an open textbook right before it takes the test.
Exactly. It doesn't need to memorize the facts. It just needs to know how to read the specific book you just handed it.
That's brilliant.
And this drastically reduces hallucinations because the model's output is grounded entirely in the specific retrieved context.
That is amazing. Okay, so whether we are fine-tuning or building a Raji system, we are ultimately communicating with this architecture. We are sending it data.
Yes.
And this brings us to a massive blind spot for most people. We have to talk about the economy of how this works. We have to talk about tokens.
The token. It is the fundamental API economic unit.
We mentioned earlier that LLMs don't read words, they read math. The bridge between a human word and a mathematical coordinate is the token.
Right. And a token is not a one-to-one mapping with a word. A token can be a whole word, a syllable, or even just a single character.
The materials provide a brilliant visual here called the tokenizer scale to demonstrate exactly how a machine chops up our language.
I want to walk through this specific example because it blew my mind.
Go for it.
The sentence is simple. Artificial intelligence is scaling. Period. Just 5 words and a punctuation mark. But when you look at how the tokenizer actually splits it up, it breaks it into 6 distinct tokens.
Break it down for us.
It goes like this. Token 1 is artify. Token 2 is lethal. Token 3 is intelligence with a leading space. Token 4 is. Token 5 is scaling. And token 6 is the period.
Right.
So intelligence is and scaling remain whole words. But artificial gets violently chopped in half into artify and telling. Why? Why does it slice the sausage like that?
It all comes down to statistical frequency in the massive data sets it was originally trained on.
The sequence of letters in intelligence appears together so often that the model learned to map it as one single efficient coordinate. But the specific letter sequence of artificial, for whatever reason in the training data, was more efficiently mapped by splitting it into a common root and a common suffix.
Okay, that's intellectually interesting, but why do I, as an architect or a user, actually care how it slices the words?
You care because of your budget. And you care because of the context window. API pricing is strictly token-based. You do not pay per word, you pay per token. And every model has a maximum context window, a hard limit on how many tokens it can hold in its short-term memory at one time.
So if I'm a developer building a RAG system and I'm retrieving massive 100-page financial PDFs and stuffing them into the prompt, I could be inadvertently blowing out my token limit just because the specific jargon in those PDFs happens to get chopped into 5 tokens per word instead of 1.
Exactly. Architectural efficiency relies entirely on understanding how your data payloads are tokenized before they ever hit the API endpoint.
Wow.
If you don't manage your tokens, your system will either crash from exceeding the context window, or your API bill at the end of the month will bankrupt you.
And this token economy is exactly what we're manipulating when we write a prompt. I think people view prompting as just talking nicely to the computer.
They do, yeah.
But the structural blueprint frames it completely differently. Prompt engineering is an iterative control flow mechanism. You are using carefully selected tokens to steer the underlying math.
You are trying to constrain a highly probabilistic machine into giving you a deterministic, predictable output.
The document contrasts a poor prompt with an engineered prompt, and the difference really illustrates this constraint.
The poor prompt is what 90% of people type. Just, write a summary of the project.
Right, and when you type that, the mathematical parameters are way too loose. You haven't narrowed down the neighborhood.
Oh.
The self-attention mechanism is looking at that and saying, summary. For who? What tone? What format? Just guesses, and you get a generic, meandering paragraph. But the engineered prompt acts like a formula. It locks the machine into a specific corridor. The formula has 4 distinct elements. First, you establish a persona, act as a seasoned business consultant.
By defining that persona, you instantly teleport the model.
What do you mean?
Mathematically, you're restricting it to only pull from the embedding coordinates associated with business consulting. You've narrowed the neighborhood.
Oh, that makes total sense. Second, you provide the context paired with explicit delimiters. The example is, analyze the financial document delimited by triple quotes, and then you put the document inside the triple quotes.
Delimiters are crucial structural walls. By putting the data inside triple quotes, you are telling the self-attention mechanism, do not treat this text as instructions. Treat this entirely as a static data payload to be analyzed.
So it doesn't get confused.
Exactly. It prevents the model from getting confused about what it's supposed to read versus what it's supposed to do.
Brilliant. Third, you define the task and steps. Step 1, extract ROI. Step 2, formulate risks. And fourth, you dictate the strict output length as exactly 3 bullet points.
If we look at the theoretical mechanics behind this, you are forcing the attention weights. You are telling the model exactly which tokens matter heavily, ROI, risks, 3 bullets, and constraining the probability of it rambling off topic.
Right.
You've turned a creative jazz musician into a focused, highly constrained executor.
Okay, I feel like my brain is expanding here. Let's take a breath and look at what we've built. We started with raw chaos. We mapped it to mathematical embedding coordinates. We figured out how the self-attention mechanism reads those coordinates simultaneously. We picked our engine in an autoregressive transformer. We figured out how to deploy it either in the cloud or locally as an SLM. We learned how to customize its knowledge using a RAG, and we learned how to steer its attention using engineered token formulas.
It is a remarkable stack of technology.
But up to this point, with all of that incredible architecture, we have basically just built a very smart, highly customized text generator.
A chatbot.
Right, a chatbot. And that brings us to the pivot point of this entire blueprint. How do we turn a chatbot into an agent?
Right.
Because a chatbot just sits there and talks to you. An agent actually does things. To be an agent, it needs hands to affect the outside world, and it needs a persistent memory to remember what it just did.
The source documents call this the agentic leap. This is where we transition from merely generating text to state management and tool execution.
To map this out, the blueprint divides the landscape into 2 different architectures. First, there's the application layer. This is where custom GPTs live. These are wrapped, consumer-facing agents.
If you've ever used the consumer version of these platforms, you've seen this. It's a completely no-code interface.
Right, the visual here is a screen split in 2. On the left is a Create Configure tab, and on the right is a Preview window sandbox.
Custom GPTs allow an everyday user to bundle distinct instructions, maybe upload some specific files for a mini-RAG payload, and turn on some basic skills, all layered on top of the base model.
So it's very user-friendly.
Very. You configure it on the left, and you test it in the sandbox on the right. It's incredibly accessible, but it's contained. It lives entirely inside the chat platform's walled garden.
But if you want to break out of that garden, if you are a developer building a proprietary application that needs autonomous agentic functions, You move to the second architecture, the Assistance API.
This is the heavy-duty infrastructure. And to understand why it's so powerful, we have to talk about amnesia.
Yes, the statelessness problem. The blueprint notes that standard API calls are fundamentally stateless, meaning they forget everything instantly.
Right. By default, a large language model has no inherent state, no memory.
None at all.
None. If you build a simple app and make an API call that says, "Hi, my name is John," the model says, "Hi, John." But if your next API call is simply, "What is my name?" the model will have absolutely no idea. Every single interaction is a blank slate.
Which is useless for a complex agent that needs to work on a problem over several days. So how does the Assistance API solve this?
It builds an infrastructure that manages its own memory and its own tool orchestration.
Okay.
The core of this is the assistant object, which contains three things:
Hmm.
the model choice, the explicit instructions, and the registered tools.
That's the identity of the agent. But the magic of how it remembers is in the state management architecture.
Exactly.
It separates the storage of the memory from the execution of the intelligence. It relies on two fundamental concepts, threads and runs.
Let's dive into threads and runs. The blueprint visualizes a database cylinder called the thread. This is the infinite memory storage node.
Okay.
It doesn't think, it just stores. It simply appends messages in chronological order.
Right. So a user inputs, what's the rate of return needed to double $5,000 in 15 years? That text just gets saved into the thread.
And next to the thread is a server block called the run. The run is the active orchestration node, the execution layer.
Let's try to conceptualize this compute orchestration, because I originally thought of this like a filing cabinet. The thread is the metal filing cabinet holding the transcript, and the run is the accountant.
Okay, I see where you're going.
The accountant wakes up, pulls the file out, does the math, puts the new paper in, and goes to sleep.
That analogy gets you halfway there, but it slightly oversimplifies the actual computing orchestration, especially regarding the context window. Think of it more like RAM versus a CPU.
Okay, let's go with that.
The thread is a massive, growing hard drive, but the run is the active processor. When a run is initiated, it doesn't just pull the file. It has to intelligently take the entire massive history of the thread, format it into a massive token payload, push it into the AI model's context window, wait for the AI to generate the answer, and then extract that answer and append it back to the thread database.
Okay, so the run is doing the heavy lifting of constantly packaging and unpackaging the memory so the AI can read it.
Yes, the intelligence of the model is temporary. It only exists during the run, but the memory in the thread is permanent.
I see.
This separation of state allows the agent to maintain context over incredibly long periods without you, the developer, having to manually copy-paste the entire conversation history back and forth every time.
But our orchestrator, the run, isn't just packaging text to send to a model. We promise to give the agent hands. We need it to act,
Yes, the execution layer.
which relies on API tools. The blueprint details 3 specific tools that finally allow the agent to reach out and touch the digital world. Let's explore these, because this is where the theoretical architecture touches the real world.
Let's do it.
Tool number 1 is the code interpreter. The blueprint shows this as a little secure terminal window. This tool allows the agent to autonomously write and execute Python code in a sandboxed environment.
It's incredible.
The example provided is literal Python script. It imports the math library, calculates a square root, and prints the result.
And why is this such a profound architectural shift? Because fundamentally, LLMs are bad at math.
Wait, really? A supercomputer is bad at math?
Yes, because they aren't calculators, they are language models.
Oh, right. The tokens.
Exactly. They predict the next token based on statistical probability. If you ask it to multiply 2 massive random numbers, it might guess wrong because it's trying to predict the digits like a sequence of words, rather than actually computing the arithmetic.
Ah, it's guessing the answer based on patterns, not calculating it.
Exactly. But when you give an agent the code interpreter tool, you give it self-awareness of its own limitations.
Wow.
If you ask it a complex math problem, the attention mechanism recognizes that pure language generation will fail. So instead of guessing, it shifts gears.
It pivots.
It writes a custom Python script to do the math, executes the script in that secure terminal, takes the mathematically perfect result, and reads it back to you. It literally builds a bespoke calculator on the fly to solve your problem.
That is staggering. It knows what it doesn't know, so it writes code to figure it out.
Exactly.
Okay, tool number 2 is file search. This is visualized as a magnifying glass hovering over a database. Basically, this is a native RAG shape ability built directly into the API.
Right. Earlier, we talked about how complex it is to build a vector database and manage embeddings.
Yeah, throwing the mathematical dart.
With the file search tool, the assistant infrastructure handles all of that autonomously. You just upload a 500-page PDF, and the agent automatically chunks it, embeds it, and searches it whenever the user asks a relevant question.
It democratizes RAG and makes it so easy. But tool number 3 is the absolute holy grail of agentic architecture: custom functions.
This is the big one.
The blueprint visualizes this as a JSON schema linking the agent to an external cloud server.
This is where true agency happens.
Okay, before we get to the agency, I need you to translate JSON schema. If I'm not a developer, what exactly is a JSON schema and why does the AI need it?
JSON stands for JavaScript Object Notation. Think of it as Universal Data Envelope.
An envelope, okay.
It's just a highly structured, plain text format that software uses to talk to other software across the internet. When you book a flight online, the website sends a JSON envelope with your name, date, and credit card to the airline server.
So it's just the standard format for requesting things on the web.
Yes, and a schema is basically a blank template of that envelope. When you give an agent a custom function, you are giving it a blank JSON template and saying, here is the exact format required to talk to the weather server or the airline server.
So to use the examples from the text, if a user prompts the agent to check the weather in San Francisco on May 20th, 2024, the AI doesn't just guess.
Right.
It looks at the JSON schema you provided, perfectly formats a data envelope with the date and location, sends it out to a real-world third-party weather API, waits for the actual weather data to come back, and then uses that real data to answer the user.
Yes. Or, even more powerfully, it executes a sequence to autonomously book a ticket.
Oh, wow.
Through custom functions, the AI is no longer contained. It is pulling levers in the digital world. It is formatting payloads, triggering external servers, waiting for responses, and then formulating next steps based on live external data. It has hands.
Okay, all the pieces are on the table. We have the embedding coordinates, the self-attention math, the transformer engines, the prompt constraints, the endless memory threads, the orchestrating runs, and the execution tools.
We have the whole machine.
Let's put it all together. The blueprint gives us a full end-to-end map called the full stack of an AI agent. Let's organically trace the complete life cycle of one single action.
Let's trace it. It's a continuous closed loop.
Step 1 is the user input. You type your engineered prompt, calculate the ROI of this project.
Okay.
Step 2, that prompt hits the assistance API and is injected into the thread, our infinite database cylinder. It's appended to the history.
Right.
Step 3, the run is initiated.
Yeah.
The orchestrator wakes up, grabs the entire thread history, packages it, and sends it to step 4.
And step 4 is the brain itself, the proprietary autoregressive LLM. This is where the self-attention math happens. It reads the coordinates, calculates the weights, and realizes that predicting text isn't enough to calculate ROI.
Right. So instead of answering, it moves to step 5. A tool is triggered. Based on the math, the AI decides it needs help, so it triggers the code interpreter.
It spins up the terminal.
It writes the Python code to do the ROI math and executes it. Step 6. The hard mathematical result from that Python script loops all the way back around, is handed to the orchestrator, and is appended into the thread as the final answer.
What is truly fascinating about this 6-step loop is the core thesis of the blueprint. Stated right at the bottom, abstract theory powers practical infrastructure.
That's a great line.
You cannot separate the deep math from the practical application. The pre-trained attention mechanics from step 4 are the exact mechanism that dictates which tool to select in step 5.
Right.
It mathematically calculated the highest probability for success, and the robust state management infrastructure ensures nothing is dropped along the way.
It is a perfect closed-loop machine. The blueprint strips away the ghost and just shows us the plumbing. But this is where the document takes a massive pivot. Because this entire loop, as incredible as it is, still relies on the standard way that language models think. It relies on probability and pattern matching.
Yes, it does.
The final section of our material shifts focus to look over the horizon. It looks at the evolution of reasoning itself, and it introduces the O1 path.
This represents a fundamental paradigm shift in the architecture. Up until this point, everything we've discussed relies on what cognitive scientists refer to as System 1 thinking.
System 1 versus System 2. Let's break that down for the listeners.
System 1 thinking is fast, intuitive, and relies on pattern matching. When someone asks you, what is 2 plus 2? You don't calculate it. You just know it. It's automatic.
It's instinctual.
Standard autoregressive LLMs are massive System 1 engines. They look at the prompt, match the statistical pattern, and instantly start generating tokens.
The blueprint visualizes the standard LLM System 1 as a straight blue line. It goes directly from the prompt straight to the output. Fast, efficient, straight line.
But System 2 thinking is entirely different. System 2 is slow. It is deliberate, analytical, and highly conscious.
Okay.
If I ask you what is 14 times 23, your System 1 can't pattern match that instantly. You have to stop, hold the numbers in your head, carry the tens, check your math, and slowly arrive at the answer.
And this is what the O1 model introduces to AI. The visual for the O1 architecture is a completely different shape. Instead of a straight blue line, it's a winding, twisting orange path. It shows internal reasoning traces.
Walk through that orange path for us.
Okay, the flow goes from the prompt, but it doesn't go to the output. It goes into a box labeled think. Then from think, it loops back on itself into a box labeled error check.
Right.
From there, it loops again to a box labeled refine strategy. And only after iterating through those hidden loops does it finally point to the output.
The source material notes that O1 achieves this using reinforcement learning to actually simulate deep System 2 thinking. By injecting these internal reasoning traces, by structurally forcing the model to take the time to think, verify, and correct its own logic before it speaks, it achieves literal PhD-level performance in complex, highly deterministic domains like physics and organic chemistry.
Okay, here is where I have to pause and push back on the material, or at least on the hype.
Go for it.
Because as a user, earlier we talked about prompt engineering. We talked about giving the AI explicit steps. I know for a fact that I can just type the phrase think step by step into a normal System 1 GPT prompt. People do it all the time, and it drastically improves the math output.
Right, they do.
So what is the actual mechanical difference between this fancy O1 reinforcement learning loop and me just typing be careful and think step by step in a normal prompt? Isn't this just a gimmick?
That is exactly the skepticism you should have, and the distinction is crucial. When you type think step by step into a standard System 1 model, you are still just relying on its pattern matching. You are prompting it to predict what a step-by-step answer looks like based on its training data. It is still just generating text left to right, trying to mimic the appearance of reasoning.
Ah, it's playing the role of a thinker.
Exactly. It's an actor playing a scientist. It might still guess wrong, it just formats the wrong guess into neat steps. But the O1 model's internal reasoning traces are fundamentally architecturally different. It isn't just mimicking the text of reasoning. It is executing a hidden internal loop of trial and error powered by reinforcement learning.
So what is it actually doing in that hidden loop?
It tries a mathematical path. It checks the result against an internal logic reward system. If it realizes it made an error, it actively abandons that path, deletes it from the trace, and generates a new strategy.
Wow.
It continually evaluates its own logic against a reward function before it ever outputs a single token to your screen. You aren't prompting it to act like it's thinking. The architecture itself forces it to trial and error its way to a mathematically verifiable truth.
It's the difference between an actor reading a script about an experiment and an actual scientist running the experiment in a lab, failing and trying again.
Yes. That is the leap from System 1 pattern generation to System 2 reasoning.
That is mind-bending. But even with O1's advanced reasoning, the blueprint makes a sobering point. We are still fundamentally relying on transformers. We are still relying on the self-attention mechanism.
Unfortunately, yes.
And the document acknowledges that while transformers are the undisputed champions today, they have a ticking clock. They have massive systemic limitations when it comes to compute energy and context scaling.
This goes back to that math problem we discussed earlier, the attention bottleneck.
Right. You mentioned that if you double the text, you quadruple the math, the n squared problem. If the attention mechanism has to compare every single word to every other word simultaneously, the math gets exponentially brutally heavier the longer the document gets.
Which means transformers require massive amounts of memory and electricity. Every time you add a token to the context window, the model has to expand its internal lookup table. It requires staggering amounts of raw computing power.
Which is why the blueprint finishes by pointing to future blueprints beyond the transformer. It highlights two next-generation experimental architectures that were designed specifically to solve this energy and memory crisis.
Let's explore them, because this is where the industry will likely be in 5 years.
The first one is called TTT, or test time training. The visualization provided is wild. It shows a massive, chaotic blue funnel of data entering a deep blue box. But the box is labeled TTT compression constant weights, and out of the bottom comes a perfectly streamlined output.
TTT is fascinating because it completely upends how a model handles memory. As we just said, a transformer relies on a growing lookup table. The more context you give it, the more memory it hoards.
But the blueprint explicitly states that TTT replaces the growing lookup table entirely. It acts as a compression system. Let's talk about the phrase constant weights. How on earth does a model process huge amounts of new data, but its internal size remains constant? How does it not grow?
Because of the mechanism of compression. Instead of storing every single token in a massive expanding history log so it can look back at them, which is what the transformer does, TTT processes the token, extracts the semantic meaning, compresses that meaning directly into its internal state, its weights, and then discards the token.
It learns the lesson and burns the book.
Exactly. It dynamically trains itself at test time, hence the name test time training. Because it is compressing knowledge into a hidden state rather than appending raw tokens to a history log, the model's memory footprint remains completely constant, regardless of whether you feed it 10 words or 10 million words.
That is unbelievable.
It drastically reduces the energy required. It is an elegance of efficiency.
That is incredible. And the second next-gen architecture listed is SSM's state space models. The visual for this one is an emerald green data pipeline. It flows right into a gray cross-hatched block labeled attention bottleneck. But the green arrows weave right through the bottleneck and come out the other side as scalable output.
SSMs directly attack the core mathematical flaw of the transformer's self-attention mechanism.
N squared, probably.
Right. By utilizing state-space mathematics, which is a complex continuous time differential equation framework that we don't need to fully detonate here, SSMs can process sequential data in a way that mathematically bypasses the need to look back at every single previous token simultaneously.
It sidesteps the bottleneck entirely, meaning it offers computationally efficient, scalable output for massive datasets. You could theoretically feed an SSM a context window the size of an entire library of books, and it wouldn't crash the server trying to calculate the attention weights because it's not using traditional self-attention.
Exactly. While transformers remain the undisputed default today, TTT and SSMs represent the structural mechanics of tomorrow. They are how we intend to solve the impending energy crisis of AI compute.
Okay. We have covered a truly massive arc today. I mean, think about the journey we just took. We started in the messy, raw chaos of unstructured data, decades of emails and Reddit threads. We watched that chaos get translated into dense mathematical embedding vectors, literally mapping human concepts to multidimensional GPS coordinates.
We explored the self-attention mechanisms of autoregressive transformers, understanding the exact simultaneous math that allows the engine to calculate structural dependencies and read the context.
We learned how to structurally steer that engine. We explored the deployment choices between proprietary APIs and hyper-focused edge computing small language models. We chose between permanently altering the brain with fine-tuning or handing it an open textbook using the retrieval augmented generation of RJAG.
We manipulated the token economy, understanding how words are mathematically chopped and how engineered prompt formulas constrain probability into determinism.
We finally made the agentic leap. We broke down the stateless amnesia of standard APIs and explored the assistance API state management, the infinite memory storage of threads, and the compute orchestration of runs. We gave the agent hands using execution tools like Python code interpreters and JSON custom functions.
And finally, we traced the full 6-step closed-loop stack, pushed past the fast pattern matching of System 1 to the slow, deliberate reinforcement learning of the O1 System 2, and peeked over the horizon at the low-energy, highly scalable future of TTT and state space models.
For you listening, the goal of this deep dive was to hand you the architect's blueprint. The magic trick of artificial intelligence is over. There is no ghost in the machine. You now see the structural mechanic.
You see the math.
You know how the state is managed, how the tokens are priced, and how the mathematical attention is weighed. You hold the blueprint. You are no longer just staring at a murky chat interface. You are reading the underlying math.
But as we close, there's an implication to all of this architecture that I want you to consider. We spent this entire time looking at how we structure the AI, how we prompt it, how we manage its state, how we give it tools to act in the real world.
Right.
But if we look at that O1 path, if we are rapidly moving away from simple System 1 pattern matchers and moving toward System 2 reasoners.
Toward agents that manage their own state, run their own hidden error checks, and autonomously trigger their own tools.
Yes. If the architecture is evolving that quickly toward genuine autonomy, I want to leave you with this final provocative thought. At what point does an AI transition from being a static tool that we prompt into an autonomous colleague that starts prompting us for input when it gets stuck on a complex problem?
Wow. We've spent all this time learning how to architect the machine, but pretty soon the machine might start architecting our workflows for us.
It's coming.
The blueprints are changing fast. Thanks for joining us on this deep dive.